Hello. Sorry for the delay there. Uh, and yes, please say hello in the chat. All right. While you're doing that, let's jump right into it. So last time we were talking about electromagnetic waves and intensity. So just a brief reminder on that before we move on to polarization and reflection and refraction. So we said the Poynting vector is 1 over mu naught E cross B. So for an electromagnetic wave, we would have something like this. E is E naught I hat cosine kz minus omega t. Similarly for B. And so just doing the cross product, we end up with this expression for the Poynting vector. The intensity is the time average of the Poynting vector. So how do we do that? So often we denote averages of some quantity by putting these angular brackets around it. Actually, that should be a vector S, but the intensity really is the magnitude of this time averaged S vector. So the only time dependent part is the cosine squared. So how do we take the time average? We integrate it over one period of oscillation, right? This is an oscillating electric and magnetic field, so an oscillating S vector. So we integrate that over one time period and then divide by the time period. So it's the time average of cosine squared. And it turns out this ends up being 1/2. Right? We can do the math if needed, but this ends up being 1/2. So we end up with 1/2, 1 over mu naught, E naught, B naught, K hat. And we can express it entirely in terms of B naught. If we remember that for an electromagnetic wave, E naught, B naught is, E naught is equal to C, B naught. Or we can express it in terms of E naught. So yeah, here I've replaced B naught with E naught over C and gotten to this. And I can get rid of the mu naught by using this relationship between mu naught, epsilon naught, and the speed of light in vacuum, C. So we end up with this. And this is somewhat familiar looking because this was that same expression we got for energy, well, almost the same expression we got for energy density in the electric field in a capacitor. The only difference is this factor of C over here. So just focusing on the magnitude, usually we talk of intensity as a scalar. Then we have 1/2 C epsilon naught times E naught squared. Any questions before I move on to polarization?
For the B, just in general, for like if you're looking at a wave for the electric field and the B field, you wrote it in terms of cosine, but like, how do you know if it's in terms of cosine or sine? Because we've seen it in terms of both.
Exactly, yes. You need more information. So for example, you might remember on the Friday's activity, you would be told that, oh, at the origin, at t equals 0, the electric field is 0. So then that tells you that, oh, it's going to be a sine wave. Or you might be told that, like, oh, at this point, at this time, it's at its maximum, and then figure out the angle from that.
Oh, okay. So we can't like automatically just know.
You can't automatically say. Other questions? Okay. So polarization, let me share my screen. Get all that. Yes, okay. So,
Okay, I have one more question. So I in this case is intensity and not current,
That is correct, yes.
but they both use the same I.
Unfortunately, yes.
Okay, I just wanted to make that clear.
All right, so so what is polarization? So the idea is that we will focus on the direction in which the E field is oscillating. So really we still have both E field and B field, right? But I'm going to focus just on what the E field is doing. So until now, we've been assuming that, oh, okay, the E field is just oscillating along a fixed direction. So here it's oscillating in the vertical direction as the wave is propagating like so. And so this is an example of linearly polarized light. What other kinds of polarization can we have? We can also have circularly polarized light, where as the light propagates, you can see that the electric field vector actually turns in a circle, but the light is propagating at the same time. So you get this kind of corkscrew for the electric field vectors. If you pass circularly polarized light through an optical element called quarter wave plate, you can turn it into linear polarized light. But yeah, won't get too much into that. And then you can have also elliptically polarized light, which is fairly similar to circularly polarized light. The difference being that as the electric field vector rotates, its magnitude changes. So you can see that it's shorter over here, and then it gets longer, and then it gets shorter again, and then it'll get longer again, and so on. So why is polarization interesting? It turns out that certain materials interact with polarized light in different ways. So unpolarized light, we often denote as just a mix of polarizations. So you will often just see it being denoted as a whole bunch of arrows like this. So this is a typical way of denoting unpolarized light. And what happens is that there are materials called, hold on, make sure that's visible there. Up a little bit, okay. There are materials that you can send unpolarized, you can have unpolarized light be incident on them. And what they will do is they will only let one polarization through. So that is, they will preferentially absorb or reflect electric field vectors in some directions and only let one plane of polarization through the material. So that is how we can go from unpolarized light, which is typically the light we get from the sun or from a light bulb or any hot object. And then you pass it through a polarizer and you can get polarized light. Question?
Yeah, okay, so what are these? Are these the electric field vectors?
Yes, these are the electric field vectors, yeah. The red arrows, yeah.
Okay.
Other questions? Okay. So let's get an idea of what happens. So if I have, yeah, okay, yeah, let's just go to slide. Okay, so all right, majority vote says 0.5 I naught will be transmitted, and this is correct. So what is happening here? So what is going on is All right, so let me come back to this unpolarized to polarized case in a moment. First, we're going to look at what happens when you just have polarized light passing through a polarizer. All right, and then we'll see what happens here. So I'm not going to poll this one, I'm just going to explain this. So supposing I have vertically polarized light of some intensity I naught, and it's passing through a polarizer, and this polarizer has a transmission axis, which is in this case inclined at 30 degrees to the vertical. So what is going to happen to the light? So the two things, interesting things are going to happen. One is the intensity is going to go down. So what we will have is the transmitted intensity is going to be equal to the incident intensity times cosine squared theta. Okay, let's clarify a few things here. Well, okay, yeah. So the name of this is Malice's law, M-A-L-U-S. The theta here is angle between polarization axis and the transmission axis. All right, so in this case, we see that the angle is 30 degrees, and so we would get cosine squared of 30, which I think is 0.75. Cosine 30 is, right, root 3 over 2, so then if you square it, you get 0.75. So only 75% of the light will be able to pass through. The other thing that happens when the light passes through is that the transmitted light is now polarized along that 30-degree angle. Put that there, 30 degrees. Okay. Any questions about this?
So the polarization angle becomes the new, so the
transmission angle becomes the new angle of polarization, yes.
okay. What happens if there's more than one?
If there's more than one polarizer, yes, we'll look at these questions. But basically the idea is that you repeat this step by step.
Okay, I meant if there's more than one initial like polar, like initial, so if all the light isn't initially polarized in one direction, say there's two,
Right.
do they
Okay,
all
so
become the same, but it goes through one polarizer, will all still go into one angle?
Yep. So
Okay.
all right, if we go back to the unpolarized example here, then again, yes, all the light that comes through is going to be now polarized at this 30-degree. Well, in this case, it was vertical over here. So in this example, it would be all vertically polarized.
Okay.
And the reason why it's, in this case, it would be only 1/2 I naught is because, well, we have all possible different angles here. And so when we look at what comes through, we need to basically take the average of cosine squared theta over all angles. So in other words, we're doing cosine squared theta d theta 0 to 2 pi, and then divided by 2 pi. And it turns out that this average is 1/2. right? Because the component which is already along the vertical will get completely transmitted because there you're dealing with cosine of 0. It's already along the right angle, so it'll be completely transmitted. The one which is horizontally polarized will not get transmitted at all because you have cosine of 90, which is 0. The one which is 45 degrees will be partially transmitted, 30 degrees partially transmitted, so on. And so if you take the average over all the possible angles, you get 1/2. Questions? All right. So let's try two polarizers. All right. So majority vote for 0.0625, and that is correct. So the idea is when it passes through the first polarizer, the angle between the polarization and the transmission axis is 60 degrees. And so the transmitted light will drop to cosine squared 60 and will come out of this first polarizer with polarization along this 30-degree angle. And then it passes through the second polarizer. And again, it makes an angle of 60 degrees with that polarizer. So you get another factor of cosine squared 60. And so it first drops to a quarter and then one more time by a quarter. And now after the second polarizer, the polarization will be horizontal. Questions? Right. So why is this happening? So it turns out what's going on, if I go back to the previous one here, what's going on is it's really related to the electric field. So this is really where Malus's law comes from. So what happens is that we can, in the original light, the electric field is oscillating in the y direction, right? And what we can do is we can split that up into a component which is along the transmission axis and a component which is perpendicular to the transmission axis. So how much is along the transmission axis? Well, if this is an angle theta, and so if this original electric field was E naught, then the transmitted one will be E naught cosine theta. Right. So what the polarizer does, sorry, I should move this really to after the polarizer. Well, okay, right now at this point, both components are present, and then after the polarizer, only the component parallel to the 30-degree line is present. So we have that E naught cosine theta 1 is present. So we see that the total electric field magnitude has dropped. And remember that we showed that the intensity is proportional to the square of the electric field. And so we get that the transmitted intensity is going to be the incident intensity times cosine squared theta. Questions?
From before, why are you showing that the E has a Y axis, has an X component when it doesn't? Like, how are you able to split it up this way?
How am I able to split it up this way? Well, remember, like any vector, so I can, yeah, let me just change color here. Right, I can have, well, actually, let me use an arrow, that'll be easier. Right, I can have a vector like this, and a vector like this, and then what is their result? It can be straight up.
Right. Okay. So this before the polarizer, what have you drawn then? I guess I'm confused what this is.
So I've just re-expressed this electric field, right? It's still there, pointing up. I've just re-expressed it as it's the sum of this electric field plus this electric field. I mean,
oh, okay.
Yeah, it's the sum of this one plus this one.
So, why are there two electric fields?
Because to get back this original vector, I need, so let me just draw that arrow.
Right. I mean, I get that, like, these two vectors would make.
Yeah. Okay. Yeah. Ignore that last one. Right. These two vectors make this one, right? So I can express the blue vector as the sum of these two pink ones, but only the one which is parallel to this transmission axis will get through.
Okay.
Right. So the reason why I'm expressing this blue vector in terms of the pink ones is because then I can see exactly how much will get through.
I see.
Right, I'm expressing it in terms of, these aren't arbitrarily chosen pink vectors. It's one vector has to be parallel to the transmission axis, one has to be perpendicular to the transmission axis.
Okay, but they're not in terms of like X and Y vectors.
No.
Okay.
It's in terms of the transmission axis.
Okay, that makes sense.
Other questions? Okay. So, all right, so that pretty much gives you the idea on polarization. And I've included the slides building off of that question in the pre-lecture, and you can, later today, the answer slides will be released, so you can take a look at that. But you've got the basic idea now. If we're going from unpolarized to polarized, we get a drop of 50% in the intensity. And then after that, as we go through each polarizer, we have to apply Malice's law again and again to see how much gets through. And the reason behind this is because of the electric field. Actually, yes. So one quick question here. Right, so here we have metal grating, right? It's just metal rods soldered onto a frame, and we're sending microwaves through. And microwaves, well, they're just electromagnetic radiation. So we can talk about the polarization of microwaves. So we send unpolarized beam microwaves through this filter. And so which one will make it through? All right. And any last votes? And stop. All right. So overwhelming vote for the vertical polarization. Some of you suspected trap, and you were correct. It was a trap. So, all right. So why? What's going on here? I didn't say that this was the transmission axis of the filter. Okay, it does act as a filter. And how does it act as a filter? That is the question. So the idea is that we send, hold on, we send unpolarized light through, right? So we have unpolarized light, which is oscillating in all these different directions. And remember that light is composed of electric and magnetic fields. And electric fields can move charges. So what happens, what happens as the light passes through the filter is the ones which are aligned with the metal bars, those electric fields are going to drive currents in these metal rods. So they're going to drive a current up and down. And that is basically going to cause those electric field vectors to reflect. Right, so those will go back or either reflect or they'll be absorbed because when you're driving a current that takes up some energy and so you lose some energy that way. But the ones which are instead perpendicular to the rods can't drive much of a current. And so those will pass through unimpeded. So this is actually a filter with a transmission axis which is horizontal. Now, we're used to polarizers, like for example, in sunglasses. So how do those work? Because we don't have like little metal rods there. Instead though, what we have are little polymer molecules which are conductive and which respond to the electric field in the light. And so the electric field in the light will actually drive electron motion in these polymer molecules, and they play the same role as these metal bars here for the microwave filter, and they will cut polarization in some directions and allow it through in others. And it turns out that if you have light reflecting off a surface, that will tend to partially polarize the reflected light, right? So, and that polarization tends to be horizontal polarization, simply because it's reflecting off of a horizontal surface. And so if you arrange your polarizer in the sunglasses appropriately, you will be able to cut a lot of the glare that comes off of this reflected light. And in fact, that is used, for example, over here in photography also. So let me just zoom in there a little bit. Right, so here you can see the same photo taken twice. One is just no filter. So it's a photo of a pond, but you can see a lot of the reflection of the sky. And the second photo is taken with a polarizing filter. And that because the reflected light is partially polarized, if you orient your filter correctly, you can block all that reflected light and only let the light from the bottom of the pool or the pool in general through. And so you get a much clearer photo of what lies inside the pool. So polarization is not just used in photography and sunglasses. It's used in a lot of different areas. For example, circular polarization is being looked at to increase the transmission of information in fiber optics, because you can have different levels of circular polarization and try and cram in more signal in the same fiber. It's used in different types of microscopy to get high contrast images. And in fact, a few years ago, I believe there was, well, that was for a slightly different type of microscopy, but basically all these properties of light can be used to highlight and increase the contrast when looking at, for example, biological samples. Questions? Yes.
Okay, I guess, so I understand like polarization when it's in different, like when it's horizontal, vertical, or like when it's on XY plane, or, but I guess I don't really understand what circular polarization is.
So circular polarization, I mean, so circular polarization, we would have, oops. Right. As the wave propagates, the electric field is rotating. So you can have it rotating clockwise or counterclockwise, and tend to call it left-handed circular polarization or right-handed circular polarization. Now, if you try to send that through a linear polarizer, that will just convert it into linearly polarized light. So yeah.
So is it, before it's circularly polarized, is it rotating both ways?
No, so if it's circularly polarized, that's different from unpolarized. it is rotating in one definite direction, either all clockwise or all counterclockwise.
Okay, so when it's unpolarized, is it not rotating at all?
You can look at it as a mix of both left and right polarization, and also linear polarization. It's really like a mix of all the possible polarizations.
Okay.
Okay, so we'll stop with polarization there and move on to more straight up optics. So, let's go back here. All right, so start with the easy stuff, reflection. So you have a light ray, it bounces off a mirror and reflects. And the idea is that what we typically do in optics is that, so the incoming ray we call the incident ray, and here we have a reflected ray as well. And what we do is at the point of incidence, right, where the light hits the mirror, we draw a line perpendicular to the surface, so perpendicular to the mirror here. So we call this the normal. And we tend to measure our angles from the normal to the light ray. So theta I here is the angle of incidence, and that will be measured from the normal to the incident ray. Theta R here is the reflection angle, so that's measured from the normal to the reflected ray. And the law of reflection simply states that theta I is equal to theta R. So what happens with the plane mirror, we see that, well, we have some object here, maybe a light bulb, and you have multiple rays coming from it, and they reflect at slightly different angles each, right? Because they didn't come in at the same angle. And so they reflect, and eventually they'll go to our eye, and our eye will focus them. We'll talk about that in a little bit. And what do we see in the mirror? We see an image of the object. We see it as if it was behind the mirror. And the way we can figure that out geometrically is if we look at these reflected rays and then trace them back, what we see is that they appear to be coming from a single point, right? And so that is called the virtual image of the object. So a couple of things here. One is for a plane mirror, we see that the image is as far behind the mirror as the actual object is in front of it. So S and S prime here are going to be equal in magnitude. And the other thing we note is, why do we call it a virtual image? Because there's, if we put a piece of paper behind the mirror, we don't actually see anything there, right? Light rays never actually pass through this image. Yeah, if it's a trick played by your brain that the light rays simply seem to come from there, then we call that a virtual image. Okay, so so that's a plane mirror. If we have not just a point object, but some extended object, then well, each point of the object that we're seeing has light rays coming from it. So these are the light rays from the top of the tree, these are light rays from the bottom. And what we see is that to go into your eye, they have to reflect off of different parts of the mirror. And then the same thing happens as before. We can trace them backward into these virtual image points, and so we see the entire tree. The reason why I'm emphasizing that they reflect off of different parts of the mirror then is that if I cover part of the mirror, right, if I yeah, if I just block off this part of the mirror, then these light rays won't reflect into my eye. And so I won't see the top of the tree, but I will still see the bottom of the tree. Right? So it only partially blocks the image in this case. Question?
When you're talking about like light rays,
Mm-hmm.
what is like a light ray? Is that like the like in terms of like waves? Because
It's yeah, it's the electric and magnetic fields moving together. Yeah.
so is it like, is the ray in the same direction as like the propagation?
Yes, that's right.
Okay.
Other questions? Okay. So clear that. All right. Besides reflection, however, because we often deal with transparent materials like glass or water, so we also talk about refraction. So typically when a light ray is incident on an interface between two media, so you have medium 1 and medium 2, then what happens is that some of the light is reflected, and that obeys the usual law of reflection. But some of the light is transmitted through into the next medium, and so we call that a refracted ray. And similarly, again, with the normal, we can define an angle of refraction. It turns out that, well, the angle of refraction is not the same as the angle of incidence, typically, and they are related to each other by what we call the refractive index, which we denote as n. So here, n1 is the refractive index of medium 1, n2 is the refractive index of medium 2, and theta 1 and theta 2 are the angles in those media. And so Snell's law, or the law of refraction, tells us that n1 sine theta 1 is equal to n2 sine theta 2. So it's named after a Dutch astronomer called Snellius, but it was actually discovered several times by different people, including much earlier than Snellius. The Persian scientist Ibn Sal actually was one of the earliest people to come up with this mathematical relation. And even before that, Ptolemy came close, but not quite to this relation. So what do we understand from this law of refraction? We see that if your n becomes larger, your angle becomes smaller. So in this case, medium 2 has a larger refractive index than medium 1, and so the angle is smaller. And so we say that the light has been bent towards the normal. Now, of course, we can always send the light ray the other way, going from a high refractive index to a low refractive index, in which case the light ray is now bent away from the normal. Okay. So supposing you send it light ray through a slab of material, you will see, okay, there's a light ray, it gets bent towards the normal. Here it's going from air to glass. Air, we take the refractive index to be typically 1. It's actually a little bit greater than 1. It's like 1.003. Vacuum has an exact refractive index of 1. But for practical purposes, we'll just say that air has a refractive index of 1. And glass, it depends on the type of glass, but often we'll use a sort of average value of 1.5 for the refractive index. Question, is it proportional to density? Density definitely plays a role, but it's not the only factor that comes into it. But it's true that density and thus temperature play a role in the refractive index. So you can actually monitor the change in temperature or density of a transparent material by looking at how its refractive index changes, if you know its behavior in advance. So here it's going from air to glass to air. And we see that, okay, the light ray bends towards the normal and then bends back away from the normal when it exits. And in fact, the final ray will be parallel to the first incident ray. All right. This one is obvious, so I'll skip this one. Here we can see that clearly the refracted angle is much smaller, so NB is going to be greater than NA. What happens to the speed of light? What happens to the wavelength? So yeah, I'll just tell you some of the stuff. The wavelength is going to go to a smaller wavelength. Whoops. So the wavelength will now become lambda over n. The frequency stays the same. But then we know that the speed of the wave is lambda times f. So what we find is that here is going to be lambda prime times f. So that's going to be c over n. So the speed of light actually drops as it enters another medium. And so since n is 1 for vacuum, that is the highest speed that light has. Light is fastest in vacuum, but then when it enters air or glass or water, it slows down. So you're familiar, of course, with the sort of pop culture thing that, oh, nothing can travel faster than light. This is true, but it's nothing can travel faster than light in vacuum. You can have things that travel faster than light in water or in glass. And in fact, something interesting happens when that takes place. If you have a charged particle traveling through air or water, actually, let's talk about water. If you have a charged particle traveling through water at a speed faster than the speed of light in water, it actually gives off radiation called Cherenkov radiation. And if you've ever seen a picture of the inside of a nuclear reactor, where they have like the nuclear fuel rods, and this is kind of like soft blue glow of the nuclear rods placed in water, that glow is actually Cherenkov radiation. It's caused by particles traveling through the water faster than the speed of light. So it's kind of like the equivalent of a sonic boom, but for light instead of sound, when you have something traveling faster than light in a medium. All right. Clear that. So we'll skip over that. So one interesting thing that happens if you have light going from a higher refractive index like water to air, we know that the light is going to bend away from the normal. Well, okay, if it's incident straight up, the angle of incidence is 0 in this case because there's no angle with the normal. So sine of 0 is 0, so it comes out at the same 0, so there's no deflection straight here. As we change the angle, we see that, okay, the light ray bends away from the normal, and eventually you get to a point where the refracted ray is now parallel to the surface. And so this is called the critical angle where this happens. And now what happens if you increase your angle of incidence even further than that, right? So this is the critical angle here. And so now you can see that over here, I've increased the angle even further than the critical angle. What happens now is, well, it can't refract into the air anymore. It was already like right at the boundary in at the critical angle. So now it will just completely reflect. And so this is called total internal reflection. And this phenomena is actually used, it occurs in lots of places and it's used in lots of places. This is what makes optical fibers work. So fiber optics is based along this. You basically have light bouncing inside a narrow glass fiber because it's surrounded by a coating which has a lower refractive index. and the angle of the light is such that it just is always greater than the critical angle, so it just keeps bouncing. This is also what is behind a mirage in the desert, or not even in the desert. If you're just driving on a hot day, you can see a reflection of maybe the car in front of you, or maybe of the sky. And basically there, the hot air near the road surface has a much lower refractive index. And so light which was heading downward, as it passes through the layers of air, so let's say the layers of air with different refractive indices, then as the light passes downward, it ends up bending away from the normal until it just reflects and then comes back up to your eye. So your eye thinks that, oh, this light ray must have come from down here. And so it looks like you've seen the reflection of something in a pool of water, but there isn't any water there. All right, that is it for today. Stick around if you have questions, but otherwise, thanks.
Professor, I have a question about like the height. So for example, if the height of the medium is smaller, then most of the light is going to be completely reflected inside, right?
If the height of the medium is smaller.
Like on this picture, for example.
Oh, I see. Okay. If it is emitting in all directions, yeah, and then if the height is smaller, then well, I mean, you'd have to look at the share of the angle.
Mm.
Yeah. So you're correct that like there'll be a cone. There'll be an angle, like all the light within this cone will make it through, and then everything outside of that cone will not. I mean,
Okay.
will be reflected. Yeah.
Thank you.
Mm-hmm. Other questions? Anyone else?